Right, well, welcome everyone. Hopefully you can all hear me in the back there. Everyone good sound-wise? Okay, great. So welcome. Thanks very much for coming and making it for today's session. I'm going to talk a little bit about big data antipatterns. And I'm going to be posting the slides later tonight. So if you want to follow me on Twitter, then you'll have a link to the slides later. But in any case, I'm a software engineer. I've been working on distributed systems now for a few years. I have a book called Hadoop in Practice that kind of contains some real-world kind of recipes for working with Hadoop. And I have a blog that I've been pretty bad about maintaining, but maybe I'll get back to writing some articles at some point. But in any case, why should we care about antipatterns, right? And specifically big data antipatterns? Well, this is an example of a real-world antipattern in action. So, here it's kind of common to overload things beyond their kind of maximum capacity, and then you have undesired outcomes like this, right? Which we all can probably agree is probably a bad thing to happen. So by understanding antipatterns, we not only learn about practices to avoid, but in the process we learn more about how our tools work, and including their limitations. So here's the agenda. It's kind of a mixed bag of items. There's some higher-level antipatterns, including there'll be some antipatterns where we're going to look at some Java code, look at some algorithms, and look at some system internals as well. So hopefully there's a little bit for everyone here. But the kind of general theme is we'll identify an antipattern, we'll look at why they should kind of are bad in practice, and then hopefully look at some mitigations that will help you avoid them. And I'm going to try and make this kind of lighthearted. So there's kind of two main actors in this role. You've got Alex, who looks a little like me, but it's not me, even though we share the same name, I promise. And he's kind of new to big data. He's got a lot of enthusiasm, and he kind of reads a lot of blogs about what all the cool kids are doing. And then there's Jade. She's a seasoned professional. She's been running big data applications successfully in production for quite a few years. So let's look at our first antipattern, and it's called It's Big Data. And this one's a little tongue-in-cheek and a little lighthearted, but it's something I have encountered quite a few times. So here we have Alex saying, I have some user data, and I want to calculate some basic statistics of that user data. I need a Hadoop cluster to do this, right? And Jade is asking, well, how much data are we talking about here? And he's like, it's big data, it's 20 gigs. So what's the problem? I mean, this one's kind of apparent to us all, but there's some valuable lessons here. So as Jade is kind of pointing out, you think you have big data, but you really don't. This is big data. This is your scale of data. It's a little different. And to kind of bring the point home, I'm going to run a little quiz now. So what do you think is a maximum amount of RAM that a single rack-mounted server can contain these days in our data center? Who thinks it's 256 gigs? No one, okay. How about 512 gigs? No one? Okay. 1 terabyte? Okay, there's a few. Well, you're all wrong. That was a trick quiz. So there's this kind of neat little website called yourdatafitsinram.com where you can put in your data size, and you can keep bumping it up and up. And what ends up happening is that you can buy servers now, and they're commodity servers that have 6 terabytes of RAM. That's amazing. And the point here is that there's a lot you can do with a single host. You don't need a cluster, and especially if your data set isn't that huge. And there's another problem here. Alex is assuming he needs to build and use a Hadoop cluster. Right? If you're new to big data, and especially Hadoop, which is complex, you're going to be spending all your time in the position of this guy trying to set it up and configure it and tuning it to the kind of work that he's trying to do. And this takes time, and it's time that you're taking away from actually trying to solve your problem here. So, the kind of bottom line here is keep it simple. Tools like MySQL, Postgres, Python, MATLAB are the kind of data scientist, kind of standard toolkits. Work great on decently large data sets, for sure 20 gigs. So simplify your tool chain. Don't be kind of, the new shiny thing isn't always the best thing to be doing with the kind of work, your data size that you're working with. Okay, so the next one is called a single tool for the job. So oftentimes when you've become familiar with a tool and, and big data, just like anything else, you kind of start suffering from the big hammer syndrome, right? Like you look around you and all the problems start looking like they're a nail, right? And you've got a one hammer that's going to kind of solve that problem. And it's not surprising, right? Like how many tools can we all be experts at, kind of understanding inside out? Not many, one or two if we're lucky. But the problem here is most big data tools are kind of designed to do one and maybe two things well. And then if you compare that number with the various types of workloads that we're trying to do today, there's a disconnect, right? The type of work we need to do is kind of extensive and varied. We're talking, it ranges from low latency lookups to batch processing to graph processing to analytics to full scans to ETL. I mean, there's no way that these one big data tool can kind of do all these things. And it's kind of a shame because in the old world, like 10, 15 years ago, we only had like one tool, right? And yeah, it had its limitations, but we were all kind of experts at using it, and we all knew where it kind of started to fall apart. So this new big data world is a little different. The sheer number here is kind of overwhelming. Each category has like 5 or more tools, and they all appear to be near identical. There's a new tool every day, and you can literally spend all your time just reading and researching the space, trying to figure out what's going to work best for you. So we need a way to kind of cut through this mess to pick the right tools for you. And this is kind of a no-brainer, but unfortunately, there is no magic bullet here. You kind of need to find the best in class for the type of the work that you're trying to do. And best in class doesn't mean new or hot. In fact, it often is quite the opposite. So here's my kind of punch list. So before you kind of start reading this and disagreeing with me on various kind of items here, this is, in my opinion, this is kind of systems that I've run in production successfully at scale for the kind of workload that I'm doing with them. So low latency lookups, Cassandra works really well. Memcache has been around for ages. It does a great job. Near real-time processing, Storm is great. Now there's a bunch of other systems out there, like newer systems like Spark Streaming and Samza and some of these other things. Storm does a pretty good job at scaling, in my experience. For interactive analytics, this may be, again, a bit of a surprise, but Vertica, Teradata, the kind of mainstays of data warehousing, they've been continuing to evolve. They do a pretty good job for data scientists and people who need kind of low latency, quick access to a lot of data. And then for full scans, ETL, batch processing, storing kind of system of record data, Hadoop, this is kind of its mainstay. This is what it does really well. And then lastly, for data moving data between data centers, between systems, Kafka is kind of where you want to be at. And I'm going to be diving into most of them kind of during the course of this presentation. But the kind of takeaway here is, unfortunately, there is no one tool that can do it all. Don't believe everything you hear or read. You're going to have to verify for yourself what tool is going to work for you. And you need to be nimble about how you test. Don't spend too much time, money, or kind of political capital investing in something that ultimately may not work for you. Okay, so let's talk about data integration. So here Alex is saying, I've got a bunch of clickstream data that my application is generating, and I need to move it into Hadoop. So he's like, great, I know how to do that. My application is producing logs. That's where all my data is. I'm going to write a little ETL thing that's going to load into Hadoop, and I'm done. Now, tomorrow, he needs to use that same data in a streaming system like Storm. So he's like, OK, well, I've already developed this kind of one ETL pipeline, so I'm going to kind of leave that alone. So I can either write to maybe something like JMS for my application, and then kind of Storm can ingest that, or my Hadoop loader can be kind of augmented to do that kind of side effect right to JMS as well. So what's the problem here? So there's a pattern emerging. You're kind of engineering one-off specific pipelines. And what you're ending up with is a rigid and inflexible kind of architecture and solution. I can guarantee if you went to your CTO with this diagram, that conversation is not going to end well. So, what we really need is something generic, a central data repository and pipeline that isolates consumers from the source, and gives new users and allows us to kind of add new users and system consumers without any work to the rest of the system. And this is really where Kafka comes into play. And Kafka was created by LinkedIn because they had this exact same problem. They had these disparate systems in production, and they were building these one-off data kind of integration pipelines, and they realized they had anti-pattern in play, and they kind of built Kafka to kind of address that. And you may be wondering, okay, so what's the big deal about Kafka? Isn't it just yet another JMS? Why invent something new, right? So what's really, the kind of the hallmark of Kafka is really its throughput. So Kafka, about a year, maybe a little more than a year ago, ran some benchmarks on a 3-node Kafka cluster, and they were able to get producers writing in at over 2 million TPS, and consumers, again, over 2 million TPS pulling from that 3-node Kafka cluster, with the average kind of latency end-to-end of 2 milliseconds. I mean, this is quite spectacular given that the hardware wasn't kind of, some high-end hardware or anything. And one of the ways that Kafka scales so well is that it keeps things really simple. It uses a kind of log-based append-only file storage on disk, which is kind of very simple and kind of efficient way to write data out. And then as a side effect of that, which is a huge benefit to it, it can leverage the operating system's page cache. So the producer's writing data to disk, the page cache is kind of caching that as it goes along. And assuming that your consumers can keep up with the producer, it's hitting memory and not disk. So there are a few things to look out for here. First of all, it does use Zookeeper to maintain some state, and this introduces yet another big data tool that you need to learn and how to run and operate, which is not ideal. And then that nice thing about the operating system page cache, if you have a consumer that comes along and replays data, so it's going to do a cache miss and have to hit disk, then that disk I/O is still slow, and then that's going to screw up the page cache for all the other consumers that are kind of are able to keep up the producer. So that's a challenge. And then finally, security is kind of one of the things that isn't quite there yet. So if you're in an environment where you're dealing with sensitive information, maybe Kafka is not going to work for you. So the takeaway here is, don't write your own data integration. It's going to be take you way too much time, and again take away from solving the problems that you want to be solving. And Kafka's great as a kind of lightweight, fast, scalable way of kind of moving data around your organization. Okay, so the next one is called full scans for the win. So Alex here is saying, I heard Hadoop was designed to work with huge data volumes. Great. I'm going to stick my data on Hadoop, and then I'm going to run some joins. Something like select star from some huge table, join it with some other huge table, and do some interesting kind of analytics type work. So what's the problem here? Well, first of all, Alex is right. I mean, Hadoop was designed to efficiently scan over large amounts of data. And the way it does that is it takes files, like any other regular file system, and kind of splits them up into blocks. But these blocks are large, they're hundreds of megs in size, and they get kind of distributed around the cluster and also replicated. So you have n copies of each block in your cluster. And what that means is that schedulers can actually have a lot of flexibility when they're pushing work out to the cluster. And data locality is something you'll hear a lot about in Hadoop. And it's basically the concept where you push work to where the data is located so that data reads are from local node as opposed to over the network, which is expensive. So despite Hadoop having all these goodies, it doesn't mean we can or kind of should forget about all these optimizations we've learned working with large data sets in other systems. Disk I/O is still slow. It's the biggest bottleneck we have today. And then typically on Hadoop, we tend to run on spinning hard drives. We're not on SSDs. So it's really kind of where a lot of the latency comes into our systems. So the kind of, the thing to do here is to partition data, horizontally partition data like we used to do with our databases, right? So you think about the majority of the ways by which your data is going to be accessed, and then you partition your data on disk in that way. If you aren't sure from the outset, date is a great way to get going, because for the most part, if you've got years worth of data, chances are you only want to kind of look at a subsection of that. And then it's kind of a no-brainer, but make sure that you include that in your kind of aware clause so that the query optimizer can actually dig that partition out and not scan the whole data set. Now, another interesting thing here is projections. So projections will limit the number of columns that you're working with. Why does this matter? Well, kind of modern storage engines and formats are pretty sophisticated these days. They can optimize the read path to kind of skip over chunks of data that's not being used in a query. And that means there's less data flowing through the read path, fewer objects being unmarshaled, and there's also less data that's being sent over the network when you have a distributed function like a shuffle or a join that you need to perform. The other thing that's kind of problematic is the hash join. So hash joins in Hadoop work just like they work in other databases, which is to say they're super inefficient. So imagine you've got two data sets that you want to join together. You take the join key, you hash it, you do a modulo over the number of destination processes, then you send both data sets over the network for the actual join to happen on the kind of receiving side. So the problem here is with large joins, there's a lot of data that's going across the wire, and network I/O is kind of the slowest. I mean, it's obviously slower than disk I/O for the most part, even with a lot of the fast networks we have in our data centers these days. And this is yet another reason why filters, partitions, predicates, all the things we've mentioned up until now are so important to kind of reduce the amount of data that you're kind of shipping around. So the thing we want to do here is a merge join. Now, for a merge join to work, both data sets have to be sorted on the join key. But if you do this, this makes the join stupid simple. All you got to do is stream all the data sets and do an inline merge. It's very low overhead. And it's way more efficient than the hash join. Because for the hash join, it's got to sort both data sets, push it over the network, merge them, and only then it can do the join. So it's doing a whole lot more than a merge join. So to enable that, you're going to have these bucketed, sorted data sets, and then tell your kind of query engine that you need to explicitly tell most query engines that you need to do a sort, merge, bucket, join, and I've kind of included some configs here for Hive. And finally, consider using a columnar data format like Parquet. So when you work with data where you've got a lot of columns and you're typically only using a handful of them, columnar data formats are great because they store all the columnar values contiguously on disk. So this allows the columnar storage engines the ability to dynamically pick the best compression codec for the type of column that you're actually storing. So you can actually get way better compression with these columnar data formats than you can with kind of raw primary data structures. So, the summary, this is all kind of common sense stuff, but partitioning, filtering, projecting your data, these are all things that go a long way to kind of make your work way more efficient. Taking things a step further, you've got kind of sort, merge, bucket joins, and then consider columnar data formats. Okay, let's talk about tombstones. So you may be wondering, what does a tombstone got to do with the big data, right? That's kind of weird. So let's have a look. So Alex here says he needs a fast, persistent queue. He already has Cassandra running in production. Cassandra is fast and persistent, so he's going to use that. So what is Cassandra? Well, Cassandra is a NoSQL database. It's modeled after Amazon Dynamo and Google Bigtable. It's kind of designed for scalability, fast reads and writes, and it kind of favors availability over consistency in the CAP theorem. And the nice thing about Cassandra is you can take a cluster and you can actually divide it up into sections and into regions so that you can have, like, if you've got an East Coast and a West Coast data center, half of it can be in one side of the country and another half can be on the other side of the country. And then Cassandra kind of magically takes care of keeping all the data in sync. This is huge if low latency and availability are kind of critical parts of your application. And the thing I love about Cassandra is that most NoSQL databases don't do this. And for my kind of work, this is something that I need. So what's the problem with using Cassandra as a queue? Well, queues typically need to support a high level of reads and writes. So when you delete data in Cassandra, it doesn't immediately remove that data from persistent storage. Instead, it performs a kind of soft delete where it marks deleted records with things called tombstones. So this scheme allows for very fast reads, which is kind of great for Cassandra, but they come at a cost. So the tombstones need to, when you do scans over records looking for data, these tombstones actually incur an expense and overhead when you're doing these reads. And in extreme cases like queues, there could be hundreds of thousands or millions of tombstones that are kind of getting in the way of your reads, and what you expected to be millisecond lookups are now taking seconds. And another thing that's kind of surprising in Cassandra is that deleted data by default stays around for 10 days, which is a long time, right? Now, there's good reasons for this, and the primary one is called the kind of reappearing delete. I'm going to call it a syndrome. But I would suggest you do a Google. I don't have time to unfortunately go into the details, but it's kind of just, it's worth just doing a Google search for reappearing deletes in Cassandra, and you can read a little bit about the background there and why 10 days is how long deleted data gets kept around for. But in any case, it's a long time for the kind of that tombstone data to kind of get in the way of your reads. So clearly, Alex should not be using, Cassandra for a queue should be using Kafka. That's pretty clear. But if you really have to use Cassandra, or if you just can't get away from the fact that you need to delete heavy workloads, there's a few kind of tricks that you can kind of employ to try and avoid that from happening. So what you can do is that you can basically defer deletes. So in a queue type scenario, you would have a table in Cassandra where you'd keep a list of all your consumers and their offset in a queue, and then you'd have these kind of buckets where each bucket would represent a range of time, or some number of elements that have been added to your queue, and every time that range of time gets exceeded, then you can create another bucket. And now you can build some intelligence to say, okay, I'm only going to delete old buckets when I know all my consumers have kind of moved beyond that. And this is kind of similar to how Kafka works internally as well. So the summary here is kind of be careful with Cassandra with workloads that are delete heavy, and design your schema and read patterns to avoid hitting these tombstones. Okay, so let's now talk about Java and its built-in collections. And kind of full disclosure, I'm not a mathematician. It's been a long time since I've been in school and studying that stuff, so bear with me, you've been warned. But Alex here is saying, I want to count the distinct number of users that have viewed a tweet, right? So he cracks out his ID and says, okay, this is simple. I've got a method called count distinct users. There's an iterable of strings representing my user IDs being sent entered. I'm going to create a hash set. It should be lambda, but it's not. I'm going to iterate through these users. I'm going to add them to my hash set. I'm going to return back the size. So what's the problem with this? Well, this guy is the problem with this. And one of the biggest challenges when building big data apps is the impact of internet scale, and specifically data skew, which is caused by people like Mr. Bieber over here. So 99.99999% of your tweets are just going to have a handful of views. But there's going to be outliers like this guy whose tweets will have millions of views. So now I've got a little pop quiz for you guys again. So he's used hash set. So what do you guys think is used beneath the scenes in a hash set? So how many people think, so assuming it's of type K, right? It's a generic. How many people think it's an array of type K? Nobody. Okay, good. How many people think there's maybe some sort of kind of a wrapper around the K, but it's still ultimately an array? Okay, good. How many people think it's a hash map? Okay, and then how many people think it's a tree map? Okay, there's a few. So you're all mostly right. Good job. I'm impressed. So yes, indeed, hash set uses hash map internally. And you may be wondering, like, what's the big deal? And what's the big deal about doing that? Well, hash map has a pretty big memory footprint, and it's a chained hash table implementation. And these map entries are kind of heavyweight things that kind of get dragged around in a hash set. And there's some math you can do. So if we assume that the average username is 6 characters long, that's about 64 bytes. So you already get a lot of explosion just using that kind of Java strings. And then there's a kind of formula that you can use to figure out how much space your hash set is occupying. So how many items you've added to your hash set is multiplied by 32 bytes. And then the array internally is multiplied by 4 bytes, and they're both added together. So what that means, the net effect here is that if you've got 10 million users and the average length of the username is 6 characters, that's 1 gigabyte of data. So that's obviously expensive, and takes up a lot of space. So there's a kind of a neat algorithm called hyperloglog that helps kind of solve this problem. And it gives you an approximate count. So it's not going to give you a precise count, so you're not going to want to use this for financial data, but it works really well. So just to give you a sense, 1 billion distinct elements occupies 1.5 kilobits of memory. So think back to the hash set, right? 10 million occupied 1 gig, and now we're talking about two orders of magnitude more, occupying 1.5 kilobits, right? That's a pretty nice savings there. So to give you a sense of how it works beneath the scenes, imagine that you wanted to estimate the number of times a coin was flipped, right? So one way that we could do that is to kind of count the longest number of runs of a head that we saw in a row. So for example, if you're flipping a coin and you tell me that you've seen a maximum of 2 heads in a row, I'm going to guess you've not been flipping that coin for too long. But if you've been flipping a coin, you tell me you've seen 100 tails in a row, then you've been flipping that coin probably the whole day. And the way hyperlog works, it's kind of the same thing, the same principle, apart from it applies it to hash codes. So a good hash function is one where the bits of the output value are independent and each have an equal probability of occurring, kind of like flipping a coin. So this random, uniform kind of distribution allows you to extract a probability distribution for a likely occurrence. So if we were to hash 8 unique things, then one of them will likely start with 0, 0, 1. And then we can invert this. So if in a sequence of hashes, the maximum number of leading zeros is 2, then there's a good probability that we've seen 8 things. Now, to kind of improve on this estimate, the hyperlog algorithm stores many estimators instead of just one, and then kind of averages the result. And this is kind of called stochastic averaging. But what happens is we take the hash code, we kind of split into 2, and the least significant bits are used as a kind of offset into this register, and then the remainder we count the number of leading zeros, we add 1, and then we take the maximum of that and whatever's already in the register and store that value back in the register. And then we take a harmonic mean of all these values, it's kind of a fancy mean, and that basically ends up being the hyperlog kind of estimated count for your elements. It's kind of a neat algorithm. Now, there's a very nice implementation of that from Newstar called Java HLL. And the thing I like about this is that it's accurate with small cardinalities because it maintains a hashed data structure for kind of small accounts, and then it transparently transforms it to hyperlog when a certain threshold is reached. And there's a couple of other things that may be interesting here. So count min sketch is kind of an approximate accounting multi-map, so it can support top K. And then Bloom filter is an approximate set membership data structure, which is used in Cassandra and HBase and other kind of NoSQL databases as an optimization to determine whether or not data may exist on disk or not. So kind of the summary here is data skews of reality. Watch out for Justin Bieber in your data. Don't use Java built-in collections if you're dealing with super large counts, and then look at some of these approximate estimation algorithms if you're indeed dealing at that kind of scale. So I'm going to back away from the math now, and hopefully I didn't offend anyone in the process here. Okay, so this is the last anti-pattern, and it's called It's Open. So Alex here is releasing a new kind of big data application into production. He's done the prototyping, he's done the coding, he's done the testing, P&S testing, monitoring. He's ready to ship. So what's the problem here? So the problem is, imagine someone today had access to your data center. How secure would your data be? And how secure would it be from not only someone stealing it, but corrupting it or deleting it? And the trouble with a lot of the big data tools is that they're so complex that we tend to spend our time kind of wrestling with them to design our way out of their limitations, and we kind of forget that security is as important as anything else, if not more important. The other problem is that a lot of the big data tools out there just have little or no security built in, or it's so complex that it just kind of, is intimidating and no one bothers in turning it on. And then again, it's kind of a shame because in the old world, things were like super simple. Our databases had authentication, authorization, ACLs built in, and we even employed people to kind of manage them and make sure that these policies were kept current, up to date. And Alex may think, well, security is not my job, right? Why should I be doing this stuff? But hopefully you have some InfoSec people in your organization, and they're probably going to disagree with you. So the important questions to ask here are things like, is my data encrypted when it's in motion on the ether? Is it encrypted on disk? What kind of ACLs are in place to kind of make sure that only the right people have access to the right data? And is this stuff turned on by default? So here's a kind of little chart kind of comparing some of the kind of tools I've talked about so far. Unsurprisingly, Oracle gets full stars, and we're on Oracle world, so we have to say that. But it's been around for a while, so we kind of expect it to get full stars, and it does here. Hadoop does pretty well here. I mean, it's got all the kind of basic security things, but it's really complex to set up and install. So as a result, there's a lot of people running it in production that just don't have it turned on, which is kind of scary. Cassandra, again, does a pretty good job. It's pretty easy to use, but it's not turned on by default. Zookeeper, not the best. It doesn't have at-rest encryption. And then Kafka is kind of the outlier where it really, does really poorly here. And, so you've got a couple of choices with Kafka, right? You can either decide to kind of encrypt your data prior to sending it to Kafka and then deal with, unpacking on the other end, or you live with the fact that your data is not protected, or you use some other tool that, is maybe going to give you the security kind of things that you need. So takeaway here is kind of enable security, please. It's an important part of kind of evaluating a tool, and if your product or kind of vendor doesn't support it, have a discussion with them and ask them when it's going to appear on the roadmap. Okay, so we're done. So the kind of general themes here were, don't assume that a big data technology is going to work for your specific use case. Kind of test it out in your own hardware and data. I mean, that's kind of common sense. And be wary of the new hotness. I mean, all the vendors, they all claim that they can scale to vast amount of data, but you'll be surprised when you ask them the hard question of, okay, what kind of scale testing have you done in-house? They'll oftentimes, we're talking about hundreds of gigs of data, which to me isn't big data. So, ask hard questions about your vendor, and if they say they haven't scaled at scale, tested at scale, ask them why. And then just make sure that kind of scale testing is a required part of your kind of, go to production plan. So that's it. Thank you for your time, everyone. Any questions? Yes, sir. HBase. Well, so I've kind of highlighted tools that I've had experience with here. I've heard horror stories about HBase, but I've heard horror stories about everything, and I think it's now, I think a few years ago it had its problems, and now it's a lot more, I'm hearing good things about it, but I can't personally talk about it just because I don't have that experience, unfortunately. Yes, sir. So you're asking a question about keeping around system of record data. So so one of the things that Hadoop is really good at doing is keeping around a lot of data kind of reliably. Back in the day, like 10 years ago, we were all kind of bound by, we were all kind of working on single machines, and we didn't have much disk space, so we kind of naturally would have this habit of deleting data. So if, given that you don't want to be doing that with your kind of valuable things like your logs and things like that, Hadoop is probably the cheapest way today that you can store a vast amount of information reliably and securely. So when I say kind of system of record data, I mean kind of, once data becomes too big for kind of OLTP databases and even OLAP databases, Hadoop, I think, is a de facto way to kind of store data reliably over a long period of time. Yes? The question is, any thoughts about MongoDB? There's a lot of diverging opinions on, I think, MongoDB. There's a fellow out there that does a lot of kind of consistency testing with some of these kind of NoSQL tools, Jespin. If you do a search for Call Me Maybe and MongoDB, he did a search on that and found that the results were kind of interesting. I'll just leave it at that. Yes, sir. So the question was, Cassandra does the kind of behind the scenes data replication between the different regions, and have I seen any issues with that across the network? I haven't, but then I kind of, the networks that we tend to deal with are pretty fat pipes, I guess. I've not heard a whole lot of that either beyond the cases that we've had, so that would be a great question to ask maybe on the Cassandra user group. Okay, well, thank you, everyone. Appreciate your time.